Lesson 4, friction. You ready, Tanisha? Your brain's awake? Okay. Friction. Friction is due to the interlocking of molecular hills and valleys between a surface and an object on the surface. So although, for example, your lab table countertops may appear smooth, if you zoomed in on the microscopic level, Riley, you would find that it looked much more like that. And if you drag two surfaces across each other, those microscopic hills and valleys start to interlock a little bit. They resist each other. That's what resists the motion of two objects moving across from each other. It's friction. Friction resists sliding. And as such, it can resist motion if you're trying to slide an object across the floor. It can also create motion, because when you walk, friction is what pushes you forwards, which is why it's so tough to walk on ice. So example 1 says, draw the direction of friction in each case. What you really want to look at is what's happening between the two surfaces. So for a sliding block, if we're pulling it forwards, which way would friction be acting? Friction would be acting in the opposite direction of the motion of the block between the two surfaces. That's why when you slide something on ice, it's easy. When you slide something on gravel, it's tough. Okay? What about for a car speeding up? Well, you got to really follow this through and kind of zoom in on a tire. If you look at this tire and follow it this way, follow it right here, which way is the tire pushing against the pavement, forwards or backwards? It's pushing backwards, and so friction is going to act forwards because the surface is actually moving backwards relative to the pavement. That's a common mistake. People want to say, the car is moving forwards, so friction must be moving backwards. No, actually the tires, when you follow the rotation all the way around, Nathan, are moving backwards in relation to the pavement. What about for a car slowing down? So for a car slowing down, what you do is you apply the brakes, and what that does is that causes the tires to apply a force to the pavement in that direction. So which way will friction act? Backwards. We're going to talk, Curtis, about how you calculate friction, because friction can only be so big. In fact, if you need a bigger force than friction can be, and you hit the brakes, you'll skid. You'll go out of control. Because friction is saying, I'm sorry, I can't, you need a force of, I'm making this up, 100 newtons to come to a stop, and I can only be 25 newtons. I'm sorry, you've got 75 newtons of unbalanced force. You're in trouble. What does friction depend on? It depends on two things, William. The first is the type of surfaces that are in contact. You've heard me talk about ice and gravel. The rougher a surface, the more friction it has. We have a special name for this roughness. We call it, here's your new term for today, the coefficient of friction. We have a symbol for it. The symbol is the Greek letter mu. Looks like that. Greek letter mu. It's actually where our lowercase m comes from. When you write it, though, looks like that. You can imagine sort of over the thousands of years that slowly evolved into a lowercase m. Kinda. Looks like that. Sorta. A little bit. Okay? It's a dimensionless quality. What that means is, and it has no units. What do you measure mu in? Nothing. It's a ratio. If it's big, there's lots of friction. The objects are very sticky compared to each other. If it's small, not much friction. So for example, the coefficient of friction between steel and ice is about 0.01, nearly zero, not quite. Close enough that you can glide on ice for quite a while. Rubber on concrete, like your tires, 0.75. We want your tires to have fairly good friction, please. Usually coefficients of friction are between 0 and 1. If you're bigger than 1, what that really means is your glue means that you can hold your own weight and more than your own weight. So one thing that friction depends on, Riley, is the coefficient of friction. This number, and we'll almost always give it to you. The second thing that friction depends on, now a lot of students might say that friction depends on how heavy an object is. That's not quite accurate. It is true that the heavier an object, the tougher it is to push. But let's look at this table right here. If I just pull it, I have to overcome friction. Friction tugs back, friction resists me. I can make it easier to pull, though, without changing the mass of this. I can lift up as I pull. And you saw how much easier it slid? Did the mass of the table change? So friction doesn't depend on the weight of the table. It depends on something else. What did I change when I lifted up? Or how about if I'm really dumb, what if I push down at the same time as I'm pushing sideways? You can see that I can't overcome friction. I made friction so big that even though I was pushing forwards, pushing down at the same time made friction get really, really big. What force am I changing when I'm pushing down, when I'm pushing up? I'm changing a Newton's third law force. The one that we learned about last class. Which force did we call that one? That forces come in pairs. Which force? Huh? The normal force. Friction depends on two things. Mu, the coefficient of friction, how sticky the objects are compared to each other, and the normal force. In fact, Sean, stand up. Lift. What's the normal force now? Trick question. How hard is the ground pushing up now? 0. What's the friction between the ground and the table now? 0. See? That's why sometimes if it's really heavy, you don't bother pushing it, you lift it. You don't try and slide it. Good morning, sir. Got to pause my video. So, key idea, Elijah, what does friction depend on? The coefficient of friction and the normal force. That's why we spent so much time looking at the normal force last day. Jordan, there is no way to calculate the normal force directly. I will never give you a formula for the normal force. But with a good free body diagram, we can figure out how big the normal force has to be. So, consider the block below, which is being pulled by student number 1 across a rough surface. Rough surface means, hey, there's friction. At a constant speed means the forces are in balance. Suddenly, student number 2 pushes down on the block with a force F. Let's put it into something you've probably seen. You're sliding the benches across the gym. You're sliding them, and then one of your idiot friends takes a running leap and decides to sit on the bench while you're sliding it. Okay? They apply a force down. It says, if student number 1 maintains a constant applied force, what happens to the weight, the normal force, friction, and the motion of the block? Okay, let's answer all of this here. What happens to the weight of the bench? Does the mass of the bench or the mass of the block change when someone starts pushing down on it? Does the mass change? That's why I'm saying it's not how heavy an object is. That's part of it, but you can change the force required without changing the mass. What has changed? Well, what happened to the normal force? If you push down on an object, what happens to the normal force on that object? Yes. What happens to the force of friction then? Well, since friction depends on the normal force, does friction get bigger or smaller? What happens to the motion of the block? We'll come back to that. I'm going to first of all give you the equation for friction. Here is the equation for friction. Friction, and my abbreviation for friction is FFR, or FF if you really want to. I just put the R there for some reason. It's equal to mu times the normal force. Now, all things being equal, William, a lot of the time the normal force will be mg. Your normal force right now is mg. But if I want to make the question a little bit more interesting, I'll add another external force. And now William's normal force is not mg, it's something else. His mass didn't change, but I added an extra force. So friction is what times what? It's mu times the normal force. Friction is what times what? It's mu times the normal force. Is this on your formula sheet? Yeah. Most of you will memorize this one too, though, because you get tired of looking it up. So let's go back here for a second, and I'm going to, here's my free body diagram, by the way. My free body diagram says that mg and the normal force are in balance. How do I know? Because the block isn't sinking into the ground or lifting off into the air like Superman. And the fact that we are at a constant speed, what can you tell me about friction and the applied force? If we're going at a constant speed, what can you say about them? What does a constant speed mean? What's your acceleration? 0. So what's your overall net unbalanced force? What? Why? F equals what? Mass times acceleration. And what did you just tell me the acceleration was? In fact, we said winner minus loser equals F net. And we said F net is always MA. So what we're really saying here is MA is 0. Right now, or what we're really saying is this. In this first situation, if you're going at a constant speed, friction equals the applied force. Now, if friction increases, but the applied force doesn't, what can you tell me about the motion of the block? What's going to happen to the block? It's going to stop. It's going to stop. I can't remember if I did this joke with you guys or not. I was marking provincial exams for Physics 12 a few years ago. And on one of the papers, is this going to work? Come on. Come on, computer. Boy, my machine's running slow today. Oh, I don't have it pinned there either. Okay. It'll show up like 5 minutes from now. So, on one of the papers, the question said, what is the normal force? And a kid wrote this. I mean, it was funny. He got 0, but at least he knew that normal force was Fn. Okay, fair enough. Delete. Let's go back to where we were. Oh, that's not right. Friction. Right here. Friction is what times what? It's mu times the normal force. What's the normal force? We'll have to figure that out with a good free body diagram. What's mu? They'll tell us. Example 3. Turn the page. Oh, there it finally opened up. That took a while. Example 3. A student gives an old shopping cart a big push on a flat, rough surface. When they say rough surface, Elijah, what they really mean is, hey, there's friction. Which of the following is the best force diagram for the cart after the student has released it? What we're talking about then is this. I'd like you to use your imagination. Instead of a cart, we got my chair. Instead of a nice, smooth floor, imagine what would be a good example of a rough surface? Gravel. That's my fallback. So imagine gravel. Here's my shopping cart. And what we're talking about is not while I'm pushing it, but right after I let it go. Are you ready? Right there. Okay? But before it came to a stop. Boy, that thing came to a stop in a hurry. It needs to be oiled. Which of the following is the best free body diagram? Diagram A, diagram B, diagram C, or diagram D? We're going to vote. You're going to vote A, B, C, or D. You're going to vote just by raising your hand, A, B, C, or D. How high you hold your hand is how sure you are of the answer. I've worked this one out using principles of physics. I'm positive. I'm pretty sure. I'm voting because Mr. Dewick's keeping track, and if I don't vote at all, he'll make fun of me for not having any courage to vote. Okay? So, student gives an old shopping cart a big push on a flat, rough surface. Which of the following is the best force or free body diagram for the cart after the student has released it? Think about it. Who says the answer is A? 1, 2, 3, 4, 5, 6, 7, 8. Who says the answer is B? 1, 2, 3, 4, 5, 6, 7, 8, 9. Who says the answer is C? Who says the answer is D? 1, 2, 3, 4, 5. Who didn't vote at all? Did you put your hand up for one of them? So what do you think the correct answer is? Do you think the correct, B? Okay. So you need to convince me that you are right or that someone else is wrong. Throw it at me. What you got? Let's argue. Convince me that someone else is wrong or that you're right. William.
I think that B's wrong.
Convince me.
Okay, so free body diagrams show acceleration or external forces acting on something, right?
Yep.
So if everything was acting equally, then that shopping cart would just move on indefinitely.
Okay. If B was right, he's saying that would be like in outer space where you have completely balanced forces and because you do in B, yes? All your forces are balanced. So he's saying that if that was the case, the shopping cart would never stop. And Mr. Dewick, when you did the little demo up here, came to a stop even on smooth floor. Is that what you're saying? Yeah. I agree with that. So it's either A or C or D. I don't care, either or. Are you first of all, are you saying A is wrong or A is right?
Right.
A is right? Convince me.
Well, you're pushing it forward, so the force is pushing backwards.
Okay, it's after I've let go. So I'm going to argue after I've let go. Am I pushing it forwards anymore?
No,
So there should not be a force to the right after I let it go. Is that what you're saying?
like the force is the one right there.
Here's what I'm saying. Here's my argument. After I let it go, is there a force pushing it to the right anymore? Right? Because that's got a force pushing to the right. So right now we whittle it down to either A or C. Okay? Now, if C was correct, do you have any unbalanced forces horizontally? Then, Perry, wouldn't it keep going at a constant speed like outer space? Okay. You are right. Did you pick A?
Yeah.
Holy smokes. What are the forces? First of all, can you tell me what's... get the obvious ones. Okay, there's gravity. What's that one then? What did we call that? The ground pushing up. We gave that a name last day. No, okay, there's the normal force. Okay? And since there's no other vertical forces, in this case, the normal force is equal to mg. What's this one? That's friction slowing it down. That's friction slowing it down. It says, explain your answer using principles of physics. I think we just did. Yes? Go ahead.
I said D because when your wheel is moving this way, then friction is flowing the other way.
Ah, okay. So you said that. Now, that is when you have another external force. So if we go back to this picture here, what you actually have is the axle is applying a force to the wheels in order to have them apply an unbalanced force to the road. I don't think we have that here. There's no engine in this. Also, because I know it is coming to a stop, there has to be an unbalanced force to the left. Why? Because it's decelerating. It's slowing down, which means it must be accelerating to the left. Is that okay? Yep.
Doesn't really say which way you're pushing the cart, though.
Which way? It does, though. There's a direction that says motion and big arrow that says motion. Thought of that. Nice try. Yeah, I know. It was a little too big and obvious. Yeah.
If an object were to be doing what B is doing, would it be accelerating? Since the
I'd have to look. It looks like this. It looks like this arrow here is a bit longer than that arrow there. So yeah, I need more information. Or it could just be the limits of the. I think I told you. I typed this. I borrowed this from a friend of mine who typed this in Word 95 for Mac. So it could be a limitation of the 1995 graphic ability that a Mac had back then. It's pretty old. So let's try doing some physics. It says for each of the blocks below, write a vertical force equation, find the force of friction, write a horizontal force equation, find the acceleration. All right, let's try doing some of this. We have two situations. Let's do the left one first. In both of these, I gave you the coefficient of friction in the diagram. See it, mu is 0.12. So this is sticky ice. A mu of about 0.12, if you know what, that's probably about like snow. So not like ice, but slippery enough that you'd have trouble driving on it. Okay? And let's start out with a good free body diagram. What are the forces acting on this block here? Get the obvious ones. Gravity. Is this block sinking into the earth? No. Is it lifting into the air like Superman? Then I'm pretty sure there's another force in exactly the same direction, and it's the same size as gravity. There's my normal force. It looks like we have a 20 Newton, an F applied. And there is friction. Which way would I point friction? Perry? Yeah. A says, write a vertical force equation. See the vertical forces? Dylan, see them? Who's winning? It's a tie vertically. In fact, you know what? We could go winner minus loser equals 0. I think we can just say, you know what? Vertically, I'm pretty sure everything up equals everything down. The normal force is the same size as mg. There's my vertical force equation. B says, find the force of friction. Well, here's our new equation of the day. Friction is what times what? This is our new equation on the box on the previous page. Friction is what times what? Mu times the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. What? mg. So I'm going to tweak my equation to say it's actually going to be mu mg. Riley, did they give me mu, the coefficient of friction? They did, 0.12. Did they give me the mass? 10. I know g. How big is the friction force? Yeah, now's the time for your calculators. Or Or you do it in your head. You're multiplying by 10. 10 times 9.8 is 98 times 0.12. It's going to be 98 plus 1.96. I'm getting, yeesh, Mr. Dewick, 19.6, 98. 99 point, what do you get? I could be wrong. No, it's a decimal, Mr. Dewick. You get 9 point something or other? 11.76? That sounds better to me. How about we'll go 11.8 newtons. C says, write a horizontal force equation. Okay. See my horizontal forces? Who's winning? Applied force. Is the applied force bigger than friction? Yeah? What if it wasn't? Well, you wouldn't be able to get it going. I'll tell you right now. That. I am applying a force. Is the table moving? Now, I got to be careful. Friction is not bigger than the applied force in that situation. Friction's kind of weird, Zach. Friction is only as big as it needs to be. So let's suppose that this table has a force of friction of 30 newtons. That's the maximum it can have. If I pull with 10 newtons and it doesn't move, you know how big friction is? Only 10 newtons. Because if it was 30 newtons, I'd have an unbalanced force in that direction. I would be able to go like this, tug, let go, and it would slingshot over you guys. Right? Because that's what Newton's law says. So friction's kind of a weird force, Perry, in that it's as big as it needs to be. Once you've maxed it out, then you can start to slide the object. But until then, it's just going to get bigger and bigger and bigger, matching whatever you're pulling. Okay, now I can't be any bigger. Now we have an unbalanced force. We're going to accelerate. So this will accelerate, though. I see a 20. Who's winning? The 20. Let's go F applied. Who's losing? Friction. That equals MA. There's my horizontal force equation right there. What does D want me to find? Acceleration. How do I get the A by itself in that equation that I wrote in part C? Divide everything by M. So if I hear you correctly, you're saying A equals F applied minus friction divided by M. And now let's plug and chug. F applied, I've scrolled down. Was it 20? Yeah? Minus friction was 11 point. Tanisha, was it 7.6? Let's use the full value. Divided by, the mass was 10? I think I can do this in my head. 20 take away 11 is 9. Take away 0.7 is 8.3. Take away 0.6 is 8.24 divided by 10. 0.824? Someone double check me. Anyone? 0.824? I use the, did you use 11.76? Is it? 0.824? Now, Perry, did you get that? Say no. Did you put brackets around the top because there's two numbers on the top? There you go, right? Bracket, 20 minus 11.76, close bracket, then divided by 10. Let's look at the second situation. I think we'll start with a good free body diagram. What are the forces acting on this object? Get the obvious ones. Well, I'm going to have mg. Now, there's also already a force of 15 newtons down along with gravity. So I think the normal force is going to have to be bigger because it's got to cancel out gravity and it's got to cancel out that extra 15 newtons. Yes? This is a dumb way to pull something. Someone's pushing down while you're pulling. You'd never do that in real life, but this is why you would never do that in real life. Oh, and it does mention friction, and I'm pretty sure friction would be acting that way. In fact, it's possible, Riley, when I crunch the numbers, this might not move. I may find that friction is bigger than 20 newtons, in which case we're stuck. Part A says write a vertical force equation. Can you see it? How big is the normal force? It's not mg. What is the normal force canceling out? Can you see it? No, it can't be the applied force. Those aren't even the same direction. Good thought, though. It's in newtons. What's it canceling out, though? Maybe it's too obvious. It's canceling out the 15 and something else. Gravity. You know what? You know how big the normal force is? It's gravity and an extra 15 newtons. See it? We're saying everything up has to equal everything down. How do I know? Is this thing sinking into the ground like quicksand? Is it lifting into the air like Superman? Then Newton's first says those forces must be balanced. Horizontally, I don't think they're balanced, but vertically, unless we got a rocket ship or something like that, they usually are. Tanisha, what does B want me to find? Friction, what's our new equation, Tanisha? Friction is what times what? Do you remember? Mu times the normal force. I don't know the normal force. Oh, but look. I know two more forces that equal the normal force. See it in part A? This is going to be mu, which was 0.12, times mg plus 15. Friction is going to be 0.12 times 10 times 9.8 plus 15. Ten times 9.8 plus 15, and then multiply that by 0.12. Friction is 13.56 units, newtons, because it's a force. Is that okay? Yeah? C says write a horizontal force equation. Who's winning? Horizontally. Who's losing? Friction. In fact, Tanisha, do you notice that the two equations in the first example and the second example for part C are identical? Because the physics hasn't changed. What has changed is you've increased friction. How? You've increased the normal force. D. I think it's going to be the acceleration is the applied force minus friction. I think you're going to divide by the mass again to get the A by itself, yes? The applied was 20 minus 13.56 divided by 10. I can do this one in my head too, because 20 take away 13 is 7, take away 0.5 is 6.5, take away 0.6 is 6.44 divided by 10. Is it 0.644? Someone double check me. Make sure you put the top in brackets, Perry. Double check me. Is it 0.644? Don't all rush for your calculators at once for anything. 0.644? I'm right? Units? What did we just find? So what are the units? Meters per second squared. Okay. Next page. There can be friction on an object even when it's at rest, because the hills and valleys will lock up when we apply a small force to an object. The force of friction on an object at rest is called static friction. In fact, there's technically, Riley, two types of friction. There's static friction and kinetic friction. How many of you ever slid something across the floor that's heavy? Okay? Once you get it going, what do you notice about how hard you have to push? It's easier. There's two types of friction. Static friction is bigger. When something is standing still, to get it moving, the friction force that you have to overcome is a little larger. Why? Remember those microscopic hills and valleys, those microscopic peaks and valleys? They've settled into each other while they've been resting. To get it going, you've got to get it out of those peaks and valleys. But once you get it going, it kind of skips over the peaks and valleys. Like when you're going faster on a gravel road, you don't notice the bumps quite as much. Right? You hopefully experienced that. So there's two types of friction, static and kinetic. You know what? I will mention that, but I got to be honest. Most of the time, we're just going to pretend there's one type of friction to keep the math simple. But read along with me. Example 6. If we pull on a desk with a force of 2 newtons, and the desk does not move, I think that's important, then which of the following is true? A, static friction is greater than 2 newtons. B, static friction is 2 newtons. C, static friction is less than 2 newtons. D, there is no static friction. Once again, with 4 choices, Callum, we're going to vote. Once again, how high you hold your hand is how sure you are of the answer. I'm positive. I'm pretty sure. I'm only voting because Mr. Dewick is staring at me, and if I don't vote, he's going to get grumpy. Help him out, William. I'm only voting because Mr. Dewick is staring at me, so you have to vote. Are you ready? Who says the answer is A, static friction is greater than 2 newtons? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Who says the answer is B, static friction is equal to 2 newtons? 1, 2, 3, 4, 5, 6, 7. Who says the answer is C, static friction is less than 2 newtons? Who says the answer is D, there is no static friction? Boy, 14 and 7 is 21. A few of you are wimping out here. Convince me that you're wrong or that another answer... Sorry, convince me that you're right or that another answer is wrong. Michael.
I think A is right because you say friction is only as big as it has to be. So if we applied a force of 3 newtons, it still might not move.
Okay, but... yes, William.
I'm going to argue that they're both true, and then we can't tell which one with the information we have.
Argue away.
So friction is only as large as it needs to be. So if you pull on 2 newtons, the friction will be 2 newtons.
Okay, so here's my question. If I pull with 2 newtons and friction was 3 newtons,
then
what must happen?
The friction would match your pulling strength.
Well, no. Here, let's hypothetical here.
Okay.
If I pull with 2 and friction is 3, what must happen? Okay. If static friction was bigger than 2, that would mean I could do this, and it would go slingshotting over you guys. Static friction, you're right, is only as big as it needs to be. What I really mean by that is, to figure out friction, you almost always have to get there indirectly by looking at the situation. Is it moving or isn't it? Sorry, I got to be careful. Is it accelerating or isn't it? Because it could be on ice at a constant speed, which is just fine too. The correct answer, folks, here is B. Now, William, keep arguing. What if I pulled with 4 newtons and it didn't move? How big is static friction?
4.
What if I pull with 4.23 newtons and it doesn't move? How big is static friction?
That number.
4.23, exactly. What if I pull with 8.219? Static friction is 8.219. What if the biggest static friction can be is 10, and I pull with exactly 10? Still not moving. What if I pull with 10.001? I'll show you. It's exactly this. I'm increasing my force. You can't tell, but I am increasing my force. I'm increasing my force. In fact, I can feel from my fingers. I just hit there. I hit the butter zone right there. You just start to move. I matched it. You can actually feel it. You just started to match it because you can almost feel the resistance change. There it goes. Oh, and as soon as it started to move, Perry, it got way easier because now I'm into kinetic friction. Once you get it moving, it's skipping over those hills and valleys a lot easier. Oh, and the faster I get it moving, the easier, the better it is. Is that okay? Did I convince you that B is correct? It says explain your answer using principles of physics. I think we just did. Okay. Static friction acts when you have two objects at rest relative to one another. Static friction is what keeps your car with its parking brakes on a hill from rolling down the hill. Gravity wants to pull it down the hill. Static friction acts up the hill. You have an equilibrium. Your car stands still. Oh, if it's icy, you might not be able to park on the hill. Why? Static friction can't be big enough to combat gravity. Okay. A block of wood will remain stationary on a sloped table until you increase the angle sufficiently that it begins to slide. The force required to overcome static friction is always greater than the force needed to balance sliding friction, called kinetic friction. So kinetic friction, Perry pointed out, once you get it moving, it's easier. Kinetic friction is sliding friction, and it's smaller than static friction. And it is true that they are two different types of friction, and in fact, there's two different types of mu's. There's a mu static and a mu kinetic, but we're going to treat them as the same for Physics 11 and Physics 12. Next page. For what it's worth, just so you have an idea of some coefficients of friction. Coefficient of kinetic friction between wood and wood, if you're sliding wood and wood, it's about 0.25. Steel on steel is about 0.5. How can we reduce the coefficient of friction? Look at the third entry there. What do we do to reduce the coefficient of friction in our machinery? Yeah, we had oil. All oil does is it reduces the mu. It gets into those microscopic hills and valleys, and so now you're floating a little bit more, and now you slide better. Okay, so lubricated, it's about 0.1. Rubber on dry asphalt, it's anywhere from 0.4 to 0.8. It really depends on temperature and what kind of tires you have and how heavy your vehicle is. This is why, by the way, buses, big Greyhound buses, can travel in snow better than small cars. They have a bigger normal force. Friction is mu times the normal force. Rubber on wet asphalt goes down to about 0.2. Those of you that are just getting your driver's license, it has nothing to do with how good a driver you are. It's the physics. Slow down when you're in the rain. Nothing to do with your driving skill. I'm sorry. Friction is not as big as it used to be. You can't stop in the same distance that you used to. Rubber on ice, about 0.005. Steel on ice, about 0.01. These are all approximate. They vary with conditions as degrees of smoothness, with temperature, with all sorts of stuff, but rough idea. Can you have a coefficient of friction greater than 1? Yep. Glue. If I glue something to the ceiling, it can support its own weight and more than its own weight. It's got a coefficient of friction greater than 1. Not just glue, by the way. Dragster tires have a coefficient of friction greater than 1. The expensive ones, if you're doing it in the pros. Why? What force pushes a car forwards, as it turns out? Friction. So can you change the normal force of the car? No, actually, dragsters are fairly light. So what do you change, mu? Example 7. A force of 120 newtons is needed to push a box along a level road at a steady speed. You know what, Hakeem? I think we should underline the phrase. Because if you're at a steady speed, what can you tell me about my net force? Well, first of all, if you're at steady speed, what can you tell me about my net acceleration? 0. What can you tell me about my net force? 0, because force equals ma. What it really says, Perry, everything's balanced. Whatever I do for my free body diagram, everything better balance out. All my verticals better cancel out, and all my horizontals better cancel out. If the force of gravity on the box is 250 newtons, what is the coefficient of friction? Between the box and the road. This looks like a job for a free body diagram. Here's the box. What are the forces acting on this box? Get the obvious one. Gravity. Darn right. Does this question suggest that the box is sinking into the ground like quicksand? Is it lifting into the air like Superman? That must mean there's a force in the opposite direction, same size. What force? Normal force. Riley, if they don't give me a great big long arrow that has the word motion on it, we'll assume you're pushing to the right in the positive x direction. So let's assume the applied force is this way. And it's 120 newtons apparently. How do I know that this can't be it? Okay, that can't be a steady speed. There's got to be something in that direction. I can even tell you how big it is. It's 120 newtons. I can even tell you what it is. What force is that one? Ah! What are they asking me to find in this question? Sorry, got to make sure I don't hold it up backwards for you guys. Asking me to find mu. Okay. What's the equation that we have that has mu in it? Friction equals mu times the normal force. All right, let's get the mu by itself. How would I get the mu by itself? I don't know friction. Oh, I do though, because I know another force exactly the same size as friction, the applied force, which was how big? I don't know the normal force. Oh, but look. I know another force the same size as the normal force. What? mg. So it's going to be 120 divided by... Oh! You know what? They didn't give me the mass. What did they give me instead in the question? They actually gave me mg. That was nice of them. Less work. It's going to be 120 divided by 250. It's going to be 12 divided by 25. What do you get? Sorry? 0.48? 0.48 what? What are the units? There's no units. And by you know how you can tell? What are the units that I would measure friction force in? Well, it's a force. What would I measure that in? Newtons. What would I measure that in? Newtons. I have newtons divided by newtons. Oh, cancels. No units. Coefficient of friction, dimensionless. 0.48, nothing. Yep.
When you did the example of the table there, and you said that the maximum friction it could have was 10 newtons.
Yep.
If you pull with 10 newtons, it wouldn't move, right?
If I pulled with 10 newtons, that's the equilibrium point. It would either stand still, or if it was already moving, it would keep going at a constant speed in a straight line.
Moved it and then had the exact same amount of force as it could apply, then it would...
Well, so if it took me 10 newtons to just get it going, once I just got it going, because kinetic friction is smaller than static friction, it actually no longer take me quite 10 newtons. I can pull with less and keep it going. And it's hard for me not to automatically relax my hands and do that because I'm just used to pulling stuff. Good point. Next page. Coefficient of kinetic friction between a steel block and an ice rink is 0.01. If a force of 24.5 newtons keeps the steel block moving at a steady speed, what's the force of gravity on the block? You know what this looks like a job for? Free body diagram. What are the forces acting on this block? Get the obvious ones. Darn right. What else? And I think the same size, yes? What else? Friction. Okay. Let's do the applied first. Because they told me it was 24.5. I agree, friction. Why did I draw friction the same length as the applied? Pardon me? Why? See, this time I didn't give you the hint because I didn't underline something. I just let you spot it. Do you see it? Dylan, I think I heard you say steady speed. Yeah? Okay, now let's underline that because I would have if I was doing this question. That's a key concept to me. Steady speed means all of my forces are in balance. What if it wasn't a steady speed? I'd go winner minus loser, who's winning, and I'd have an MA on the other side and have to do some math. What's the force of gravity on the block? Okay. Well, I know this. Friction equals 24.5. I wrote that down because I have no idea what else to do. Oh, friction is also what times what? I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Do you see it? Ah, ha. Because what's this question asking me to find? Jordan, what's this question asking me to find? Give you a hint. Find the word what, and then read the phrase after that. Ah, force of gravity. Can you see the force of gravity anywhere in what I've written? What? Where? What? And let's get the mg by itself. How? Divide what? By? Mu. Yeah. So if I hear you correctly, Jordan, you're saying the force of gravity, which I don't know, is going to be 24.5 divided by mu, which is going to be 24.5 divided by 0.01, which I think is going to be 2,450, but double check me. Yeah? You got that on your calculator? Divide by 9.8. What's the mass? 250 even? Okay, so an extension of this would be, I could give you the same question and simply say, what's the mass of the block? And you'd have to clue in, I can't find the mass. Oh, but I can find mg. Oh, no, I can't. Oh, yeah, I can find the normal force, which is mg, which is the mass. Then I can divide by g. How much more am I doing here? One more? Okay. A group of dogs are trying to pull a 220 kilogram dog sled, but they are unable to move it. If the dogs are capable of exerting a total force of 232 newtons, what's the minimum coefficient of friction between the sled's runners and the snow? Nathan, you know what this looks like a good job for? A free body diagram. Sled. Darn right. I agree. Why did I draw friction the same size? Okay, I think they're in balance because my acceleration is 0 because we're stuck. And by the way, that's why I said minimum coefficient of friction. It's possible that these sled dogs are nowhere close to moving this. But I'm assuming that they're right on the brink. Must be, because it's not moving. So if it's not moving, what's my acceleration? And so what must my overall force be? And so everything must be in balance, right? So I think it's going to be this. Friction equals 232. Friction also equals mu times the normal force. Sam, what's this question asking me to find? I gotta be fast. You missed a key word. Coefficient of friction, not the friction force. Coefficient of friction. They want me to find mu. Okay. How would I get mu by itself? Darn right. That's a terrible mu. Dope! I don't know the normal force. Oh, but look. Another force the same size as the normal force. What? mg. So it's going to be 232 divided by mg. It's going to be 232 divided by 220 times 9.8, which is what? You get 0.1076. You're going to get a lot of time to work on this next class as well, but for now, questions that you can try. Number 1. Number 2. Number 3. Number 4. 5. Really, Mr. Duke? Yeah, 1, 2, 3, 4, 5. 8. We're going to pause there. A couple videos to show you.